Welcome to Principles of Formation Evaluation PGE 358, Spring 2020. I hope you're all happy and healthy, and I hope you're taking good care of yourselves. This is Professor Carlos Torres Verdin introducing the lecture for today. And what we're going to do is we are going to do an optional lecture so that you don't have to view this, analyze it. It's optional, but it's fun and it's interesting. And the optional lecture is going to go through some examples of shale-laminated sandstones around the world, maybe 2 or 3 cases. And we're going to look at deltaic sedimentary sequences, and we're going to look at turbidite sedimentary sequences, and we're going to look at logs, well logs, that include the vertical perpendicular to bedding plane resistivity. So we have both parallel to bedding plane resistivity, which is the normal one, and the perpendicular to bedding plane resistivity. And the idea is that you can see the differences even if the lamina are so small within the volume of investigation of the tools, that because of that difference, immediately you know that you have shale laminated sandstones. And then to analyze, to understand whether the sandstones have good storage properties, good flow properties, we are going to combine them with the magnetic resonance log. I have not talked about the magnetic resonance log yet, but it's a very interesting log that allows one to look at the pore size distribution. So if the lamina of sandstone have good pore sizes, we will be able to tell that. But if the lamina of sandstone have small pore sizes, then we're also going to be able to tell. And because of that, we will be able to assess the petrophysical quality of the interbedded layers of sandstone. That's the objective of today's small lecture. I hope you like it. It's optional. Enjoy it. Let's do it. Hello everybody, here we are with the PowerPoint presentation, but let me go really fast so that we can get to the heart of the matter in no time. So this is an optional lecture. It's not to be counted for exams or homework. It's just for the glory of improving the understanding of things. Whoever is interested in expanding knowledge, then happy to do it here. Second, we're going to talk about a couple of things, which is triaxial induction resistivity measurements in the borehole. And with those, we're going to be able to rotate the measurements into resistivities oriented parallel and perpendicular to bedding plane, which is great. Those are the resistivities that you need to calculate saturation and hydrocarbon saturation in the lamina of sandstone. And then we're going to combine them with magnetic resonance measurements. I know that I have not covered magnetic resonance measurements, so I'll give you a very quick practical introduction to them and how they're used in the context of shale-laminated sandstones for petrophysical quality. And then I'm going to talk about 2 cases of deltaic and turbidite sedimentary sequences. Both of them are part of the compendium. Just remember the orientation of the borehole in the context of the azimuth and dip of the layers is very important. When you have standard logging tools, resistivity tools, they are going to measure the electrical resistivity perpendicular to the borehole direction. But a new type of measurement, which came not long ago, a new commercial resistivity measurement, enables the measurement of electrical resistivity in the 3 orthogonal directions aligned perpendicular with respect to the borehole axis. And when you have that, then you can detect the dip and azimuth of the formations, and then you can rotate. And when you rotate, then you can have electrical resistivity measurements both parallel and perpendicular to bedding plane. And it's very important because most of these fine laminations, sandstone or shale, all of them are below the volume of investigation of the resistivity tools. So technically what we're doing is measuring an average, a directional average, if you will, of these properties. So if you have one measurement only in one direction, it will be very hard to know if in that volume of investigation they were lamina. But here we go. And just to remember, we are looking at sandstone shale laminated sequences where the commonly the thicknesses of the sandstone lamina and the shale lamina are below the volume of investigation of the measurements. And also remember that we're looking at the pure shale and member of the sequence as reference as we cover in the part 2 of these lectures. And isotropy, as I said, comes from these superfine laminations or from grain size variations that cause variability in irreducible water saturation, especially when you have hydrocarbons. So we have various types of possibilities when the rocks will exhibit electrical resistivity in isotropy. In other words, the electrical resistivity will depend on the direction that the measurement is made. Parallel, perpendicular to bedding plane, and when we have dip in azimuth, we also have a rotation. So we cover the fact before we explain that most resistivity borehole induction resistivity tools measure the electrical resistivity parallel to bedding plane, but the new ones also measure the electrical resistivity perpendicular to bedding plane. And there are two directions. Actually, there are triaxial resistivity tools, but because in some other contexts, especially when these formations are dipping at an angle, then you need the three directions of the resistivity measurement. So we have coils, induction coils, in precisely the three directions. So we have transmitters in the three directions and receivers in the three directions. So with that, you have a complete set of measurements for induction resistivity that sense the directional properties of resistivity in all three directions. And we mentioned that in specific examples when we have this situation, especially very thin lamina of sandstone and shale below the resolution of the tool, then the parallel to bedding plane resistivity will measure a value which is much lower than the electrical resistivity of the sandstone layers. The vertical resistivity, which is the resistivity perpendicular to bedding plane, will measure a little bit higher of a resistivity, but not quite the resistivity of the sandstone. So what we need to do is, with these two measurements, we need to combine them to estimate the resistivity of the sandstone. So in the previous lecture, I showed you how to do the quantification if you have only the resistivity parallel to bedding plane and when the layers are horizontal. That was very important. And I show you the equations that one is for resistivity, horizontal resistivity or resistivity parallel to bedding plane, and the other one is for resistivity perpendicular to bedding plane. In fact, if you have one measurement, you have two variables, so you have to determine the volumetric concentration of shale, and you also have to determine the resistivity of the shale. And once you know those variables, then with the measurement that we have here, we can estimate the resistivity of the sandstone, and then we can apply Arch's equation or modifications of Arch's equation to estimate the hydrocarbon saturation in the lamina of sandstone. When you have the vertical resistivity, we have a series type circuit. And in that case, we also have the common variables. And if you have the vertical resistivity, you can estimate also the sandstone resistivity. But when you have the two measurements, and you can do a system of equations in which you can have two unknowns, either the resistivity of the sandstone and the volumetric concentration of shale, or the resistivity of the sandstone and the resistivity of the shale, depending on which of the three variables you assume to be known. For instance, the volumetric concentration of shale could be calculated from the gamma ray log, and then point by point with these two equations solved simultaneously, you can estimate the resistivity of the shale and the resistivity of the sandstone. Or if you assume that the resistivity of the shale is known, then you can estimate the volumetric concentration of shale and the resistivity of sandstone. So you can apply this equation in any way you want. Now, here's a beautiful example. Again, very excited about this example where we have, it's a turbidite sedimentary sequence. Let me show you in some detail. Here we have the gamma ray log. Notice that the depth that we have here is in meters. So we have from 1,600 to 1,800. So we have 200 meters. I want to point out the maximum values of gamma ray here or at the bottom here, and also I want to point out the number of the relatively high number of oscillations of the gamma ray log per unit length, which indicates that this is a rock sequence with great variability per unit length. Now, over here, what I have is the neutron and density logs. And what is very interesting about this sequence is that it is actually saturated with heavy oil. But look at this. We don't have a crossover between neutron and density logs, despite the fact that the neutron and density logs have been expressed in the proper matrix here. So no crossover. And why is there no crossover? Most likely because these sequences are shale-laminated. So the presence of shale in non-negligible volumetric concentrations has masked the crossover between neutron and density logs, as we have seen in previous examples. It's only at the bottom where we'll begin to see some degree of crossover. But let me show you two new measurements. One, over here, we have two resistivities. One, the blue is the resistivity parallel to bedding plane, and the red color one is the resistivity perpendicular to bedding plane, similar to what I showed you before. This is just a cartoon. The values are not the same, but the idea is the same, that as soon as you see, or as soon as you have laminations where the thickness of the laminations is much smaller than the volume of investigation of the tool, boom, immediately you're going to have the separation where the resistivity of the perpendicular to bedding plane resistivity will be higher than the resistivity parallel to bedding plane resistivity. If there are no laminations, if there is no anisotropy, then the two measurements will overlap. I also want to point out that the display here is in logarithmic scale. So here, anytime, any place that you see separation between parallel to bedding plane resistivity and perpendicular to bedding plane resistivity, immediately we know that we have an isotropy. It doesn't matter where it comes from, we have an isotropy. It's a beautiful measurement. It's not so clear if you have only one measurement. Even the shells are anisotropic, as you can see here. And the degree of anisotropy is not the same. You can see that in some of the sections below 1,700 meters, the separation between parallel and perpendicular to bedding plane resistivity is not as large as what we see in the upper part. So the upper section of this example has a higher degree of anisotropy than the lower section. There are some places actually here where the two parallel and perpendicular to bedding plane resistivity overlap, which means that the rock is homogeneous. Very interesting. So now that we know that we have laminations, how can we quantify the petrophysical quality of the intervening, interspersed layers of sandstone. And here is how we do it: magnetic resonance. Magnetic resonance is the measurement here displayed with these histogram type plots. Every single depth that you see here has a plot like shown here. Every single depth, so they're all stacked. Where do they come from? Okay, the x-axis of those plots is what we call transverse relaxation time, and the vertical axis is what we call incremental porosity. Where do they come from? They come from the fact that we have proton magnetization. Protons are made to diffuse in the medium, and when they have restricted diffusion, it so happens that the time of relaxation, this is the time axis, and this is the porosity relaxation. The time of relaxation will depend on, in this example, on two things: the type of fluid and the dominant pore size. But when you have only one fluid, then this relaxation in time, please note that the x-axis is logarithmic time and the y-axis is incremental porosity. So the upper side, the asymptote at early times of this plot, is actually the porosity of the rock, and when the proton magnetization decays over time, that goes to 0. Now we have two plots here. One plot, the blue plot here, is when the rock is 100% water saturated. If you do the area, sorry, before I tell you how is this curve obtained? That curve, the blue curve, is obtained from the measurement, and the measurement is the time decay of proton magnetization. So if you fit a distribution of exponentials to explain the decay, you are going to find here that there are two dominant exponentials that explain that. One is centered at about 100 milliseconds, and the other one is centered at about 10 milliseconds. So there are two dominant exponentials that explain this decay. And of course, those exponentials are not discrete, it's more of a continuum. But let me just explain. The way this plot is done is that the area under the curve is equal to the porosity of the rock, which is the early time value of this exponential decay. And so the area under the curve is precisely that porosity. What we know is this, that the place where the maximum here takes place is an indication of the dominant pore size when you have only one fluid phase. If you have two dominant peaks like here, that means that you have two dominant pore sizes. But the amplitude of the peak is an indication of which of the two dominates on the porosity. Obviously, in this example, the large value of T, which corresponds to large values of pore sizes, is the most dominant with respect to this. Now, what is the light blue curve? Well, the light blue curve is this. We take that rock, and this is in the laboratory. This is not a borehole measurement. You centrifuge the rock, boom, and you expel all the fluids that are mobile, and you only leave the fluids that are not mobile, and then you do another magnetic resonance measurement. You see, this is the measurement right here. That's the time decay of proton magnetization. And we see that the dominant peak here takes place precisely where the second most dominant peak of the fully water saturated sample had. What does that mean? Well, it means that this peak exists, is a pore size, but the rock, the fluids, water in this case, contained in those fluids is not mobile. That's an important thing to say. It's almost like having a bimodal pore size distribution, where one of the modes is more dominant in the porosity and the second mode is less dominant in the porosity. So now let's go to the plot here. What this is the following. If you are in a shale, which is the upper part of the diagram here, the dominant times of decay are relatively small. That means that the pore sizes are relatively small. That's precisely what we see in a shale. That's the reason why shales are impermeable. If you go down at the bottom shale, you are going to see the same thing, that the dominant pore sizes are very small. Now, what happens when you go in between? When you go in between, at the very center, again, we have a shale, and the dominant pore sizes are very small. So we have 3 places for a shale. But something interesting happens in these areas right here. What is that happens? We have a second dominant peak. Because the second dominant peak takes place at later times than the peak for shale, we know that the pore sizes will be larger than the pore sizes for the shale. And why do we have this? Well, this second peak is the response of the intralayers of sandstone. And the amplitude of this peak is going to tell us whether those sandstones have good porosity. So the location of this peak is an indication of the relative pore sizes. The closer that peak gets to the shale, the smaller the pore sizes. And the farther away it gets from the shale, the larger the pore sizes. And the higher the amplitude of that peak, the higher the porosity of those sandstone layers. And you can go through here and, for instance, compare the upper section here to the lower section here. What do we see? We see that the dominant peak for the sandstones here takes place at slightly faster times than in the upper part, which means that the average pore sizes for this sand development of the intervening sandstone layers here is smaller than for the upper part. That's important. And second, we also see that the height of this peak for the lower section, the second dominant peak, the height is smaller than the height of the first peak. What is that? Well, it tells us that the porosity of these intervening sandstone layers over here is not as good as the porosity here. So the upper section has a lasagna, a sandwich, if you will, in which the sandstone layers have, number one, better porosity and larger pore sizes than the sandwich that we have in the lower section. This is very important because if you combine the parallel and perpendicular to bedding plane resistivity, that already tells you that you have a laminated sequence. And if we use the magnetic resonance measurements, then we know what is the relative petrophysical quality of the interspersed layer of sandstone. I hope you like that. And just to give you two conditions, you can have two rocks with the same porosity. Here, this is 20%, and this is 19.5, very close to 20. So we have very close porosity. But what about the permeability? The permeability is not the same. In the upper part, we have 7.5 millidarcies, and in the lower one, we have 279 millidarcies. So why is it that with the same porosity, we have different permeabilities? And the answer is because in the lower rock here, we have relatively larger pore sizes than in the upper rock. And when you look at the corresponding NMR transverse relaxation curves, the two distributions, if you compare, the area under the curve for both of them is approximately the same because the porosities are approximately the same, but the dominant peak for the lower rock takes place at longer times. And if the rocks are saturated with one fluid, this is telling us that the pore sizes for the rock at the bottom are relatively larger than for the rock at the top, and consequently the permeability is different. That's a beautiful way to indirectly estimate the petrophysical quality of the rocks, and that's possible because of these transverse magnetic relaxation measurements, which what we do is essentially all the protons contained in water, in this case in hydrogen, what they're done, they behave like magnets. We polarize them, align them, then rotate them, and then we let them go and diffuse themselves in the pore space. So they diffuse with some restricted diffusion. And the time of magnetization, the time it takes for all of them together to lose collective magnetization, is indirectly an indication of the pore sizes, and that's how we can interpret this. If you remember, we had in class this very interesting analogy. I know some people don't like it, but it's the shower head. So you can have rocks with the same porosity, but with different distribution of pore sizes, and because of that, the way in which the fluids are going to move through the pore space is going to be different. So if you have a shower head that has about the same pore sizes and large, that would be a very effective and efficient way to transport the fluids in the rock. But if you have a rock that has small pores or a variability of pores, then some of the fluids will move faster than others, and that will give discrepancies or lower efficiency for fluid transport. I hope you remember that. All right. And here's another example. This is a numerical simulation example that I want to show you. We have thin beds over here, saturated with water and hydrocarbon. And what I want to show you is this. This is a very thick bed at the bottom, and these are very thin beds. When you are in the very thick bed, you are going to see one dominant peak. Let's assume that in the very thin beds over here, you have the same quality of petrophysical quality of the sandstones as in the very thick bed. So what happens? Well, what happens is when you do the magnetic resonance, because magnetic resonance also has a volume of investigation, it's going to show the two dominant peaks. But why does it show two dominant peaks? Well, because in the same volume, we have the presence of the shales and the presence of the sandstones. And so one peak will be for the dominant pore size of the shale, and the second peak will be for the dominant pore size of the sandstone. And the height of that peak will be an indication of the porosity of the relative differences between the porosity of the shale and the porosity of the sandstone. But in this rock, you will see two peaks, but it doesn't mean that in one layer of sandstone you have the two peaks. And this is not a shower head that has small pore sizes and large pore sizes. What happens is that within the volume of investigation, you have the layers of shale and the layers of sandstone. And because of that, the response ends up looking like two dominant peaks, which doesn't mean that you have a shower head. The same sandstone layer has a shower head with small pore sizes and large pore sizes. We can have that situation, but not in this example. So when you go back to the plot that I have here, that's exactly what we are seeing in this example. So we have very thin layers of sandstone and shale, but at any given time, any given depth, we see two peaks, but that's because the layers are so thin that we're looking at the combined response of the two. But if we know how to interpret this, then we understand where they come from. And that's all, folks. Just to summarize, I have shown you that when we have these triaxial resistivity measurements, we can have access to rotated electrical resistivities. We can actually rotate the frame of reference to be aligned with the direction parallel and perpendicular to bedding plane. And when you do the rotation, that immediately gives you a very good estimate of the dip and azimuth of these layers. So this tool, the triaxial borehole induction tool, allows you to, number one, estimate the dominant dip and azimuth, and second, it allows you to rotate the electrical resistivity measurements to give you one parallel and one perpendicular to bedding plane. Last but not least, if you combine those electrical resistivity measurements with magnetic resonance measurements, then there's a very good possibility that you can estimate the petrophysical quality of the intralayers of sandstone. Excellent. Thank you. And now let's move on to the examples. Okay, welcome everybody. How are you doing? I hope you're following me. I hope this is not too complicated, but it's fun. It's actually very interesting because these are very modern measurements and instruments that I'm showing you. And to begin, on the compendium, page 358, compendium, well log compendium part 2, let's begin with page 26. On page 26, we have well logs that were acquired in a deltaic sedimentary environment offshore Egypt. Very interesting measurements. We have the caliper, we have the traditional resistivity measurements, which are the resistivities perpendicular to the borehole axis, 5 depths of investigation, and then here we have the neutron and density logs expressed in sandstone porosity units. We have looked at this before, so I'm not going to go and describe them more. But the new kid in the block, so to speak, the new thing is this particular track. And what do we have here? What we have here is the beautiful measurement of, let me zoom here, so that I tell you, these are the resistivity parallel to bedding plane, and this one, the green color one, is the resistivity perpendicular to bedding plane. The scale of the measurements, it's the same, 0.2 to 200 ohmmeters, and when I say the same, is the same as the electrical resistivity measurements perpendicular to bedding plane. Now, in this example, the measurements were not only acquired with this triaxial induction tool, but they were also rotated so that now we actually have the values parallel and perpendicular to bedding plane. This is very interesting because if you flip the page on 27, you are going to see something interesting. These are photographs of core measurements. One is a direct photograph and the other one is the ultraviolet light. Please note that the scale here is 1 foot. Definitely what we see in 1 foot here is below the resolution, below, smaller than the volume of investigation of the resistivity measurements. So all of these things are somewhat invisible. We see them because of their macroscopic effect in the directional properties. But what I want to point out is the layer in here is at an angle with respect to the borehole axis. So the traditional resistivity measurements will measure resistivity in this direction. But that's not the right resistivity to measure here. We have to rotate and ascertain the principal directions of the layering. And that's exactly what this tool does. Point by point, the sampling rate of the tool is half a foot. So every half a foot, the tool stays there and calculates with the triaxial resistivity measurements. It calculates the dip and azimuth. It rotates to those directions, and then it delivers the resistivities parallel and perpendicular to bedding plane, which is very important. Let me flip the page back to page 26. What you see here is if you compare the parallel to bedding plane resistivity here to the horizontal resistivity, you're going to see that they do not overlap in all the cases. In many cases they are the same, but in many other cases they're not the same. So it's important in this example. But the most interesting thing is that now with these two measurements, depth by depth, one can go, and because we have both, we can look at the equations of the parallel and the series resistivity circuits. And with those, we can estimate we can use a system of equations and estimate either the volumetric concentration of shale, the resistivity of the shale, and of course the resistivity of the sandstone. And with those, we can deliver a much more reliable, much more precise calculation of sandstone resistivity than using the traditional resistivity measurements. How about that? In fact, if you look at the location of the shale here, which is at the top, and at the bottom, right here, we have pure shales, you are going to see that despite the fact that these are shales, we observe a difference between the shallow and deep sensing resistivity logs. And you say, wait, is that invasion? Answer, no, it's not invasion. What's going on is that even the shale has an angle with respect to the borehole. And because of that, the measurements, the parallel to bedding plane resistivity, will exhibit discrepancies between shallow and deep, because the shallow and deep resistivity logs do not have the same volume of investigation. So they're looking at different sets or volumes of rock. When that happens, and because of the angle, we're bound to not see the same things. So no, but once we get the parallel and perpendicular to bedding plane resistivities, we immediately know that even the shales are anisotropic, because shales actually very often they are anisotropic because of this layering in which the particles orient, because of the very low energy with which they're deposited. A number of other things cause this alignment of particles, and the alignment causes macroscopic electrical resistivity. So what I want to point out is that immediately when we see differences between parallel and perpendicular to bedding plane resistivity, and please remember that this scale is logarithmic, so the differences are very large. And when that happens, when we see this, immediately we know that even though the beds are invisible to the volume of resolution, volume of investigation of these measurements, their macroscopic effect has manifested itself in the presence of electrical anisotropy. So anywhere you see a discrepancy, and please note that consistently the perpendicular to bedding plane resistivity is larger than the parallel to bedding plane resistivity. That's a very important property that we cover in the PowerPoint presentation. So anytime you see this, that's consistent with the presence of laminations. But there are certain places that we see here that separation no longer exists. And to give you one example, it will be at this particular depth, which is 10,075, approximately 10,075 feet measured depth. At that point, we observe that both the neutron and density, the parallel and perpendicular to bedding plane resistivity, they overlap. Why do they overlap? Because we do not have anisotropy. The same happens here. And why don't we have anisotropy? Because the presence of shale laminations is negligible. And lo and behold, we go to the gamma ray resistivity log, and what is that we see? Well, we see that the gamma ray log exhibits the lowest possible values in the sequence, and that is probably consistent with a clean sandstone. And so because it's a clean sandstone with no shale laminations, we observe no anisotropy right at this point. So that's a very interesting observation, but anywhere else we see anisotropy. This exercise doesn't have magnetic resonance measurements, but let me flip the pages now to show you a magnetic an example, a turbidite example that has magnetic resonance measurements, similar to what I showed you in the PowerPoint. The examples that I'm just about to show you, they are all based on a turbidite sedimentary sequence, and here we have a beautiful outcrop of channelized turbidite systems. We covered this in class, but here I'm just showing you the possible channels that we have in the system. In the outcrop, look at the massive developments. Some of them are more shale laminated than others, but for instance in this lower section we have a significant component of shale laminations because that part pertains to the bottom or lobe or distal part of the turbidite complex. And just to remind you, on page 182 we have a plot of the various elements of the turbidite system depending on whether you're close to the shoreline or in the deep bottom of the sea. But one of the things that I have said is that as you go down into the fan complex, things get more laminated, and the examples that I'm about to show you are all comprised in the distal, in the sand-shale systems that have to go with the distal part of the fan complex, which is the most shale laminated of all the systems that we have in the turbidite system. In fact, the examples that I'm showing you now, I'm about to show you, they all have the same properties as this outcrop. Please recall the thickness of the layers of shale and sandstone. The relatives, sometimes they are dipping in have an azimuth with respect to the weld trajectory. All the welds are going to be vertical, but please understand that when you have a weld that intersects these layers, we are going to have an anisotropy, so the parallel and perpendicular to bedding plane resistivities will have differences. And also, when we look at the petrophysical quality of the interspersed intervening sandstones, we are going to observe that in the magnetic resonance logs. And the pages of the compendium that I'm going to show you for this analysis go from page 173 to 176. All of these examples that I'm about to show you were plotted with about the same vertical scale. They are all vertical welds intersecting these turbidite systems, very old turbidite systems. You can actually see, first of all, the photographs of the rocks at a particular depth for reference. And also in all of these plots we have the gamma ray log on the left. Then we have the parallel and perpendicular to bedding plane resistivities. Those are the important ones, parallel and perpendicular to bedding plane resistivities. Then we have the density in neutron logs, and then we have the compression and shear sonic logs. Don't pay attention to those for the moment. And then we have the magnetic resonance log. Similar to what I show you in the PowerPoint presentation. Here we have a borehole image. In this example, the wells were drilled with an oil-based mud, so the borehole resistivity images are produced with a tool that is specific to working in oil-based muds. And then here we have a typical display of the depths and azimuths going from -10 to 40, essentially with some of these points move to the right. That means that the depth of the formation with respect to the borehole axis increases, and there's also a tadpole in these measurements that the orientation with respect to north, east, and south is telling you the direction of the azimuth of these layers. And some wells have actually core data to where the core samples have been taken to the laboratory to calculate the porosity and permeability. But the first thing that we see here, going back, is two things. The variability, the energy of the gamma ray log is already indicating that we have a high degree of laminations. And these sequences come in cycles. You can see one cycle here, another cycle here, and yet another cycle here, where the gamma ray log begins to increase toward the bottom of these cycles. So we have repetitions of turbidite distal fan complexes that are coming because of the movement of the deposition. We also see that invariably where the volumetric concentration of shale increases, we also see that the degree of anisotropy increases, the difference between the parallel and perpendicular to bedding plane. The other thing that we see observed in these examples is that despite the fact that all of these formations are saturated with heavy oil, we don't see a crossover between neutron and density logs, which is the consequence of the presence of the shale laminations. Remember, presence of shale laminations is going to mask the crossover that we would otherwise see in clean sandstones. But look at the magnetic resonance log. We have two dominant peaks in some cases, but the most important one is the peak that shows for early times, and that peak is associated with the shales that have relatively small pore sizes. And then we have the second peak here, which is an indication of the pore sizes of the intervening sandstones. And remember, the height of this peak and the location will tell us about the porosity of the sandstone layers and their dominant pore sizes. But by comparison, if you look at the sandstone developments in the three groups that we have here, you are immediately going to understand that the quality of the sandstones in the lower section is the best because the dominant peak takes place at the latest time, and also the relative amplitude of this peak is the largest among the three sections. So because of this, if you were to rank the petrophysical quality of these sandstones, you would say that the best quality is at the bottom, and maybe the second one is at the top, and the third one is at the bottom. On page 174, we have a similar display, so I'm not going to describe all of the elements of this, but again, with about the same distance, we observe important anisotropy and not so important anisotropy at the bottom of the sequence. If you compare the magnetic resonance logs, we are going to see that potentially the best sandstones are at the top. We also have sandstones with good quality, but the pore sizes are not as good as the pore sizes at the top. And then we have this intervening section that looks extremely good, comparable to what we see at the top, and then maybe the section at the bottom has sandstones, but not of the same quality. So we have a variability of sandstones here with different qualities based on the magnetic resonance log. The presence or discrepancy of resistivities parallel and perpendicular to bedding plane already unfolds and tells us with no uncertainty that we have a laminated system. But when we look at the magnetic resonance log, we immediately can compare the petrophysical quality of all the sandstones, and because of that, one can do a ranking of the petrophysical quality of the sandstones in this example. Let's go now to page 175, and in this example, if you look at the core photographs, you're going to be able to see the presence and impregnation of hydrocarbon. It's a very important point. And typically what you see is hydrocarbon, it's placed in the layers of sandstone which have the best petrophysical properties because of the migration. Now in this example, again, same properties, separation between neutron, between parallel and perpendicular to bedding plane resistivities. If you compare this example to the previous ones, you are going to see that this example is probably one of the ones that shows the least discrepancy between parallel and perpendicular to bedding plane resistivities. And if you look at the magnetic resonance log, you are going to see that in effect we have shale sandstone laminations, but in this example the petrophysical quality of the sandstones is probably the worst of the three that we have shown so far. Certainly we don't see uniformity. It's very patchy, and the values, the heights of these T2 distributions for the sandstone dominant peak are very reduced, and also the location is extremely variable. So the quality of these sandstone developments is not as good as the one that we have seen before. Moving on to page 176, what we see is probably the best sandstone development of all the examples that I have shown you before. First of all, the upper sandstone development exhibits the lowest values of gamma ray log, and when that happens, the presence of anisotropy decreases, the proximity of the neutron and density logs increases, and the typical peak for the shell member of the laminations begins to disappear, and the sandstone peak for the T2 distribution, the transverse relaxation magnetic resonance measurement, exhibits number one, the largest values, and second, the highest amplitudes of all the plots that I have shown you, all the examples that I have shown you before. All of the examples that I have shown you from pages 173 to 176, they're all located in the same reservoir system. But of all the systems, we have the best petrophysical quality here compared to the previous examples. When we go to the remaining sandstone developments here, what we see is that the anisotropy begins to increase, particularly so in the lower development of sandstone. But when we look at the magnetic resonance logs, we see that the quality of the sandstones is not nearly, the petrophysical quality of the sandstone layers here is nowhere near as good as the one for the upper layers, perhaps with the exception of this patch of sandstone that seems to exhibit very good properties. So in summary, the combination of the parallel and perpendicular to bedding plane resistivities and magnetic resonance is potentially extremely reliable for, number one, to diagnose the presence of sandstone shale laminations, and second, to assess the petrophysical quality of the sandstones, of the intervening layers of sandstone. In these developments, the porosities are relatively low. We are talking about sandstone porosities of approximately 10 to 15%. So understanding that the pore sizes are large gives us a very good opportunity for ranking, for rock classification, and the ranking itself gives the petrophysicists the ability to indicate which sandstone developments are potentially the ones that could give rise to the most dominant production in the well. And similarly, in sandstone developments whose properties are not, petrophysical properties are not very good, on occasion in this reservoir, hydraulic fracturing is used to improve the production of these developments. And when to do hydrofractures, it's based, or when or how to decide where to place the hydrofractures is on one hand determined by the petrophysical quality of the sandstones, their thickness, and so forth, so on, and is also governed by the elastic properties that can be inferred from the compression and shear sonic logs. But essentially, this combination allows the petrophysicists to rank the sandstone developments in potential production, and also the ranking allows the production engineer to design different completion operations for different sections of the well. So this is the end of the presentation. I hope you enjoyed it. It's a very relatively short presentation. I hope it's short, but the intent was to expand the topics covered in class. For those of you that are interested in learning more about shale-laminated sandstones, their implications, and how to diagnose them, and how to quantify the petrophysical quality of the sandstone layers so that we can have a better, more reliable quantitative description of their flow properties, and therefore a better indication of their financial viability. Excellent. Now we go to the next topic. Stay well, be happy, and continue to enjoy formation evaluation.